Okay, welcome back everybody. Hopefully you'll like this section a little bit better than the last one. I know the last one was pretty tricky when it came to conceptualizing these tensors and outer products. And really we put all of that work in. I'm going to jump ahead just a little bit. We put all of that work in for the following theorem, or definition I should say, which is the Taylor series in d dimensions. So it's certainly should be possible that we, if we have a function f of x, y, and z, that this function has a Taylor series like we are used to, where you have some derivatives of f here, call it f of n, nth derivative of x0, y0, z0 divided by n factorial, and then you multiply by x minus x0, y minus y0, z minus z0. But the real question becomes, what do we put up here? What do we put up here? What do we put up here? And in fact, the astute among you will know that that's not well defined for scalar fields. There's no such thing as the nth derivative of the scalar field, because there's multiple directions you can take the nth derivative in. And what should any of these powers be if I have a n factorial in the denominator? It's really not clear how to define this as an object, even though it should be well defined. And the way that you have to do it is with tensor products. So you have the nth power of the gradient, which we had just recovered in the last section as the nth tensor product of the gradient with itself. And in fact, you have the nth tensor product of the vector x minus wherever we center the Taylor series. And then you take those two tensor products. This is a tensor product on that scalar field. This is a tensor product of the actual vectors. You take them together and you take the scalar product. So we've got, n outer products. We've got n outer products. And then we have the scalar product in the middle. So it's the fact that we had to define our outer products for two separate sections, one of them being on the gradient, the other just being on vectors, and then define the scalar product of two of these tensors. We're getting infinitely high in powers of tensors here when we have the Taylor series. And then you compute the scalar product of the two of them, you end up with a scalar, right? Because phi is scalar valued, it's a scalar field. So this is really, not a trivial definition to make. It requires some pretty deep understanding of tensors, even though it has a really elegant notation. And that's why we spent that entire last section really covering what tensor fields were and higher powers of the gradient operator. So that's why I'm calling this section the Taylor series in d dimensions. But we start out just as a nice recollection. Maybe it's been a while since you were working too hard with Taylor series in Calc 2. How do we define the Taylor series of a function even in one dimension? So we're going to stick to one dimension right away. We're going to say, hey, f's going to be this function that maps the real numbers to the real numbers, and we're going to call it analytic. Now, in fact, analytic is a tautological requirement for the Taylor series. We define the analytic functions, the ones which have Taylor series. But the Taylor series of f centered at some point, okay, don't forget that all Taylor series have a center. And the center is just something that somebody tells you, they ask you to center it somewhere. And that center shows up right here, and it shows up right here. Okay, so the center shows up in two places. And then you can construct the Taylor series the same way with everything else. So the Taylor series is always you compute n derivatives of f, evaluate it at the center. This is why the center is important. We have to know where we are evaluating the derivative. And then you multiply by nth powers of x minus the center. So we've shifted ourselves to the center. That's what x minus the center means. And finally, you divide by n factorial. For those of you who forgot the definition of factorial, this is n times n minus 1 times n minus 2 times 2 times 1. With 0 factorial defined as 1. So that is the process of the Taylor series. So what do we actually have to do to compute these is we just compute n derivatives and then evaluate them at a specific point. So I've got two examples here. Neither of them are very easy, so you should thank me for actually typing all of this up because it took forever. So these examples, the first one is, it seems easy on its surface, 1 divided by 1 minus sine of x. And we're going to center it at x naught equals 0. And we want to do this maybe through quartic terms. So quartic would be x to the 4th power. So we're going to find this Taylor series centered at x equals 0 through quartic terms. I'm not going to go through all these computations with you, but the idea is that, hey, if we're going through quartic terms, we need derivatives of f through the 4th derivative. Okay? So we're going to go ahead and compute 4 derivatives of f The first one, or the 0th is here, it's f itself. The first is here. I've used a lovely quotient rule and simplified. The second, I get to use a couple quotient rules. The third, I get to use even more quotient rules and product rules, etc., etc. This is kind of an excuse for everybody to get good at using their derivative rules once again, because maybe it's been a little while. And the fourth ends up looking pretty insane, but actually when you simplify it, you only have 4 terms. It's not that bad. But yeah, these computations by hand were horrendous. But the important thing is that, okay, so I've computed my 4 derivatives of f. If I'm going through quartic terms, what I need to do is actually evaluate them. So I evaluate the 0th derivative at 0, the first derivative at 0, the second derivative at 0, the third at 0, and the fourth at 0. Recall I'm evaluating at 0 because somebody told me that the center is 0. Okay, so we care about the center. That's where we evaluate everything. We go ahead and evaluate those. Sine of 0 is 0 and cosine of 0 is 1. And we get 1, 2, we get 1, 1, 2, 5, and 16 as our coefficients. These are the coefficients showing up right here. So I just computed those numbers. Now I can reconstruct by using the factorials. There's my factorials. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. And so you just evaluate those, and we end up with 1, 2, 3, 4, 5 coefficients. They exactly go 1, 2, 3, 4, 5 as the coefficients in my Taylor series. So that's the expansion up to quartic terms for 1 divided by 1 minus sine x. We've got another example here where I've chosen a new center so that you don't get too comfortable with your results just having an x power. The results, if I move the center, the results need to have powers that have been shifted by the center. So these are going to be in terms of x minus 1. This function is going to be sine of log of x. I'm going to give it the name g. I'm going to compute, since I'm going to go through quadratic terms here, somebody's going to tell you how many terms you need to compute through, but quadratic terms here, that means I have to go through the second derivative of g. And if I do that, the 0th derivative is the function itself. First derivative, we have a beautiful chain rule. The second derivative, we have a beautiful product and chain rule. And we can simplify that a little bit. We then have to recall that what is my center? My center is 1, which means I'm evaluating my previous answers at 1. There should be a good space here. So two separate numbers there. So I'm evaluating each of my derivatives at the center, which is 1, and I get the numbers 0, 1, and -1. And then I need to incorporate my factorials, 0 factorial, 1 factorial, and 2 factorial to get my 3 coefficients. These are the coefficients of 0, 1, and -1/2, which means I can reconstruct my Taylor series using these coefficients of 0, 1, and -1/2. There's my 3 coefficients against powers of x that have been shifted by the center, right? We've shifted by the center, x naught equals 1. Okay, so hopefully that's your quick and dirty reintroduction into the Taylor series, because I know how easy it is to forget things. Now we're back to what I started this video with. This is the Taylor series in d dimensions. Our life gets much, much more difficult when we've jumped up to d dimensions. It's more difficult because that is a tensor, and this is a tensor. And so instead of just computing a lot of derivatives, we compute a lot of derivatives. We're going to see that now. But I'm going to introduce really quick, what do the powers of the outer product of x minus x0 look like? Well, if I give the vector x the name x1 through xd, and I give x0 the name x01 through x0d, right, this is vector x0, then the outer product of that difference with itself, what am I looking at? This is the first entry squared. This is the first, use a different color, it's the first entry times the second entry, right? First entry times the second entry. This is because this is the first row, second column of the matrix. This is the first row, dth column of the matrix. What are the 2 entries that multiply? It's the first entry and the dth entry. Okay, so it's really not that bad. You just have to choose which row and which column of your matrix you're in, and then go over to here and grab those entries and multiply them together. This is where you get the higher powers. But it certainly gets tricky when I jump up to 3, right? If I jumped up to 3, then all of a sudden it's like that nice thing with partial derivatives where this matrix needs to exist in 3 dimensions, and I get something like this out here, and way in the back we have something like probably like, what is it, x1 minus x01 squared xd minus x0d or something like that. It goes in the far back or whatever. So it gets tricky when we do something like a third power. So we do have to be pretty careful about these Taylor series. Now, with that said, we finished the section just with 2 examples of this. Okay, so as long as we get content with our next 2 examples of these Taylor series, boom, we're already moving on to the next section. So all I'm trying to do today is get us used to calculating these Taylor series in higher dimensions. I'm going to take my time going through the next 2 examples. So let's look at the following function. It says x1 squared plus 2x1 x2 plus x2 squared minus cosine of x1 plus x3. And now, what is a center for a scalar field? The center is going to be a vector. You can interpret that as a vector if you'd like to. This is the vector 1, 0, negative 1. Right? A center for a scalar field is now a vector because the inputs to a scalar field are a vector. So I'm centering myself at a vector now. I've got my scalar field defined. What do I need to do to calculate the Taylor series? What do I need to do to calculate this? Well, what did I say? I set up to quadratic terms. So keep in mind quadratic, we're looking through the second power of x, which is thankfully the one that I've already displayed for you, so I don't have to think too hard about it. What do I need to do for the Taylor series? If I'm going through quadratic, well, I need to calculate this. Gamma 0 of phi, I'll calculate gamma 1 of phi, and I'll calculate gamma squared of phi. Gamma 0 will be a scalar. Gamma 1 will be a vector. Gamma. I've been saying gamma this whole time. Nabla 0, the gradient, will be a scalar. Nabla to the first power will be a vector. Nabla squared will be a matrix, right? So we've got the scalar, the vector, and the matrix. We're going to have to calculate those. Let's just go for it. So the scalar's not too bad. Scalar, because it's the nabla to the 0th power, I'm going to be taking 0 derivatives of the scalar field I care about. And once I take my 0 derivatives, I evaluate at the center. Evaluate at center. So I'm evaluating 0 derivatives at the center. What does that do? Well, it says, hey, that's x1. So every x1 is going to become 1. It says, hey, that's x2. Every x2 is going to become 0. Hey, that's x3. Every x3 is going to become negative 1. And what do I end up with? I end up with 1 squared. 2 times 1 times 0. 0 squared. This is cosine of 0, which, by the way, cosine of 0 is 1. So I've got 1 plus 0 minus 1 gives me 0. So that is how I would calculate the first term. And the first coefficient in the Taylor series. Second coefficient, our life gets a little trickier, right? Because this is nabla to the first power. It's going to be a vector. I now compute the vector, partial x1, partial x2, partial x3, on the scalar field here. And I just have to go through some partial derivatives. So partial derivative of x1 squared with respect to x1 is 2x1. Partial derivative of 2x1 x2 with respect to x1 is 2x2. Partial derivative of x2 with respect to x1 is going to be 0, so there's a plus 0 hiding in there. Partial derivative of negative cosine x1 plus x3, there's going to be, I'm just looking at the derivative of cosine, which is negative sine, so I have a negative sign, I end up with a positive sign. So that's my derivative in x1, partial derivative in x1. That needs to be evaluated somewhere, right? It's evaluated at my center. So I evaluate at 1 for x1, there's a 1, there's a 1. I evaluate at 0 for x2, there's a 0 for x2, and I evaluate at negative 1 for x3. Sine of 0 is 0, so that's gone, I end up with 2. Now, my second entry in the gradient is partial derivative with x2. So partial derivative of x1 with respect to x2 is 0. Partial derivative of 2x1 x2 with respect to x2 is 2x1. There it is. Partial derivative of x2 squared with respect to x2 is 2x2. And the partial derivative of this cosine, since there are no x2 terms, is going to be another 0. I've got the derivatives there, and there they are. Once again, I evaluate at the center, which means x1 is 1, x2 is 0, x3 is negative 1, and I end up with 2 times 1 plus 0 is 2. Finally, I'm computing partial derivatives of my scalar field with respect to x3. That term doesn't depend on x3. That term doesn't depend on x3. That term doesn't depend on x3. Cosine will once again become negative. Sine, we end up with my positive sign. Evaluate at the center. That's a 1 for x1, a 0 for x2, and a negative 1 for x3. Sine of 0 is 0. So that's where I end up with my nabla to the first power of phi evaluated at my center. And that's where I end up with the first order Taylor series term. I repeat the second order. My life has gotten a little bit trickier because what is this? What is the second power of the gradient? Well, this is the whole x1, right? So partial x1, partial x1, partial x1, partial x2, partial x1, partial x3, partial x2, partial x1, partial x2, partial x2, partial x2, partial x3, partial x3, partial x1, partial x3, partial x2, partial x3, partial x3, right? It's that Hessian matrix, as we would say. But I can make my life a little bit easier than that because I do not have to just go ahead and calculate these second derivatives of everything. I can actually think about this, right? This is the nice thing about how powers work. I can think about this power actually as the gradient outer product with the first derivative, right? Gradient outer product gradient, because I've already calculated the first derivative, I'm looking at gradient outer product of my previous calculation. So now I'm just going to do all, let's think about what the outer product is. It's going to be all partial derivatives of my first entry, all partial derivatives of my second entry, and all partial derivatives of my third entry. So I'm just going to look at the three entries from before, and then I'm going to compute all partial derivatives of those. So just isolating the first entry, let's do partial x1 of here. Well, I get a 2, I get a 0, and I get a cosine x1. There's a 2, there's a cosine x1 plus x3. Great. Now if I do partial x2 on here, I get that's gone, that's gone. They don't depend on x2, I just get a 2. Now if I do partial x3 on here, that's gone, that's gone. I should get cosine of x1 plus x3. And there they are. I then step down to the middle term and do all possible partial derivatives. So if I do one against x1, I'm getting a 2. If I do one against x2, I'm getting a 2. If I do one against x3, I'm getting a 0. Finally, all possible partial derivatives here. Partial in x1 gives me a cosine. Partial in x2 gives me a 0. Partial in x3 is going to give me a cosine again. So that's how I'm going to go ahead and compute those second order terms in my higher order Taylor series. Higher dimensional Taylor series. And now I have to go ahead and do the extra work of evaluate at the center. So for each of these 9 terms, I'm going to evaluate at the center. x1 is 1, x2 is 0, x3 is negative 1. So x1 is 1, x2 is 0, x3 is negative 1. 2 plus cosine of 0 is 3. That doesn't even depend on anything, so that's just a 2. This is going to be cosine of 1 minus 1. It's just going to be 1. Go down here, doesn't depend on anything, doesn't depend on anything, doesn't depend on anything. They just come along for the ride. Here I've got cosine of 1 minus 1, which is 1. Here I've got 0. Here I've got cosine of 1 minus 1, which is 1. And so there I've computed all of my first 3 tensors of my scalar field, the first 3 derivatives of my Taylor field, or I guess the 0th first and second derivative. And then I'm going to remark, I'm going to calculate what actually does this look like? What does x minus x vector at 0 look like to the nth power, right? Because x is x1, x2, x3, x0 is the center. So what is my center? My center is 1, 0, negative 1. And so I have this vector that I'm going to be computing outer products of. So I need the nth power of that vector. I'm going to go ahead and compute them. The 0th power of any vector, luckily, is just the scalar value 1. The first power of any vector is just the vector itself. So my life gets pretty easy for the first 2, but the third one's a little bit tricky, right? Here I'm taking the square outer product of this vector. So I'm looking for all combinations of entries with themselves. And what do I mean by that? Well, we can just see it as it's 1. The first entry by the first entry is going in the first spot. That's that entry squared. The first entry times the second entry is in the second spot. It's the first times the second. The first times the third is over here. We've got the second times the first over here. The second times the second here. The second times the third here. The third times the first here. The third times the second here. And the third times the third here. So we calculate all of those out and we get our lovely tensor product of the vector with itself. Now let's keep in mind what was the whole point of this Taylor series is that now we end up taking scalar products, right? It's a scalar product of this with this. It's a scalar product of this with this. And it's a scalar product of this with this. And there's factorial. So it's the first one times 1 over 0 factorial, the second one times 1 over 1 factorial, and the third one times 1 over 2 factorial. And so we just compute those 3 scalar products what do we get? When we compute them, we get, there's our first scalar product, second scalar product, and third scalar product. But what do we get? We actually evaluate, and we just get this lovely, nice long polynomial in the variables. It'll always be a polynomial. Polynomial up through quadratic terms in variables x1, x2, x3, right? So there's not really an easy way of knowing that this would be the Taylor series of the function in question until we go ahead and compute outer products. And so this is why I had to stress outer products and tensor products in the last section, because there's just not a way to compute these otherwise. I mean, there technically is, but you have to be very, very clever about making sure you do everything right. And I think this way makes it very formal, as well as gives us a very nice, explicit Taylor series in higher dimensions that that really mimics the Taylor series for one dimension. So we're going to go to the next one, the next example, and basically, you may ask why this is even useful. Well, you know, if we have something like cosine of sine of y times x, and we want to solve a differential equation equal to this function, this is actually a really hard function to solve questions about, but polynomials are much easier. And so if we could produce the Taylor series of a function like this, up to like 4 terms, 5 terms, then we get a really good approximation by solving the PDE against this function rather than, or against the polynomial rather than solving the PDE against this function. And so somebody may ask you, what is a power series expansion up to quintic terms of that function? And we're going to go through that one as well. So we're gonna compute some of these higher order derivatives for this function now as variables of y and x, and we're going to go through x to the 5th power, and we're going to center it at 0, 0. Okay, so we're going to center this at 0, 0, which means what do we need if we're going through quintic terms? We need the 0th power of the gradient, the 1st power of the gradient, the 2nd, the 3rd, the 4th, and the 5th, which is going to start to get insane. And this is why computers are incredibly useful. Computers can calculate these much faster than we can. And in fact, computers have absolutely no problem at all with tensors. Computers and multidimensional arrays, they are perfect at solving them. So if we can get good with coding, right, now that we've moved into the 21st century, we've really been able to numerically approximate some problems really, really well, because computers can solve these Taylor series out to 50 terms, and they have no problem whatsoever. So let's actually do the first 2 by hand, and then I'll say that the computer did the 3rd, 4th, and 5th for me. But let's do the first 2 through the 2nd by hand. The first one's really not bad at all, right? Because the 0th power is still just the identity. And so we just have the function we care about itself. We're going to evaluate it at 0, 0. That's a 0 for x, 0 for y, 0 for x, 0 for y of cosine of 0, which is 1. I'm going to compute the gradient, which you'll recall is the partial in x and the partial in y. The partial in x gives me a chain rule with the sign coming out on the outside. The partial in y gives me a chain rule with a cosine of y coming on the outside. Okay? So then we end up with negative sine of yx, and then multiply by sine of y, and then negative sine of yx times cosine y. They both get, once again, evaluated at the center, because that's the center, and I put a 0 in, 0 in, 0 in, 0 in, 0 in, 0 in, and we immediately recover 0, 0. Once again, when I get to the Hessian, this is the second power of the gradient. The Hessian is going to be this ugly matrix of partial x, partial x, partial x, partial y, partial y, partial x, partial y, partial y. And I don't want to have to take 2 derivatives 4 times of that. What I'd rather do is look at what I came up with earlier and compute partial x here. If I do that, my chain rule gives me the following. If I compute partial y here instead, I will have a product rule. That's why there's a plus sign there, and I get the following. If I compute a partial x of this term, I get, once again, a chain rule in the first case. If I compute partial y of the second term, then I get a product rule. I get the following. Okay, so I compute all of those using the chain and product rule, and they once again need to be evaluated at the center. Once I go ahead and evaluate at the center, it's actually quite surprising that I still get 0, 0, 0, 0. This is because all of the signs that you see, right? Sine of 0 is 0. So I'm getting so many zeros here. And then I went ahead and had a computer calculate the 3rd, 4th, and 5th for me. And when I had a computer calculate the 3rd, 4th, and 5th, what do I have? The 3rd is all zeros. The 5th is all zeros. But the fourth, there's one specific situation when the fourth is non-zero. It's actually equal to -2 for a specific collection of these 4 tensors, right? This is a 4 tensor because it's got index by I, by J, by K, and by L. It's because it's a 4th power, so it's going to be a 4 tensor. And those are all going to take values between 1 and 2. Why do they take values between 1 and 2? Because there are 2 variables, right? 2 variables. We have an X and a Y. The fact that there are 4 indexes is because it's a 4th tensor. So that's where these values are coming from. And in fact, it equals -2 in exactly quite a few of these cases. It's the cases where I plus J plus K plus L is 6. So the case where out of these bottom 4 entries, if I add them together, they're taking the values 1 or 2, they add to 6. Turns out there's exactly 6 of these where they add to 6. And it's all combinations where 2 of them equal 1 and 2 of them equal 2. I want to describe how we would come up with this tensor or scalar product of 2 tensors, right? So over here I have these 6 situations that have been turned on. These are all -2 for these cases. And this scalar product against the vector to the 4th power, if I actually compute that, what is it saying? It's 0 everywhere except when the index, these correspond to the index on x, y to the 4th, which means what is a 1 with respect to these indexes? A 1 is an x with respect to indexing. 1's an x, 2's a y. 2's a y with respect to the indexing. So this is x, x, y, y, x, y, x, y, x, y, y, x, y, y, x, 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 y, x, y, y, x, x, y, and you add all of them together, and they all got multiplied by the value of the tensor there. So I have a -2, a -2, a -2, a -2, a -2, and a -2. What we end up with when I actually add all these together, thankfully multiplication is commutative, and these all give me x squared, y squared. They give me 6 copies of x squared, y squared, and there's my -2. So I end up with -2 times 6 divided by 4 factorial, which is the same as -12 over 24, which is the same as -1/2 x squared, y squared. So in fact, this is the first non-zero term, except for my scalar value term here. There's a scalar value term that's non-zero. Otherwise, I have zeros, zeros. My computer told me I had zeros and zeros. My first non-zero term is all terms of -1/2 x squared, y squared. So all the way through quintic terms, I have the following. Went through all that work just to say that cosine of sine y x is approximately 1 minus 1/2 x squared, y squared. But now you can imagine how much easier that function is to play with, how many better properties you can use that function for than cosine of sine of y times x. It's so much trickier than 1 minus 1/2 x squared, y squared. We can see how good this approximation is by plotting it. Here's me plotting it. The quintic approximation is there in red. So everything in red on the plot is what I just came up with. Everything in gray in the plot is what the true function looks like. You can see they really do agree very well for most of the space. You start to have a little bit of non-approximations at the 4 corners there. But aside from that, this is a really, really close approximation, which has made our life easier. If I wanted to find maybe the roots, right? It doesn't make sense to say roots in higher dimensions, but if I wanted to set this equal to 0 and ask where it was equal to 0, that's when 1/2 x squared, y squared is equal to 1, or when x squared, y squared is equal to 2, or when xy is equal to plus or minus root 2, or when y is equal to plus or minus root 2 over x. So this immediately tells me where I'm equal to 0, which, by the way, is some sort of hyperbola, which you could about imagine there'd be some hyperbola here where this is equal to 0. It's probably around here. So these hyperbola where it's running into 0. That's going to be a really good approximation for where the function actually reaches 0. So that's why these are important. Unfortunately, you have to go through that crazy amount of work with tensor products and computing derivatives to arrive at the answers. But anyway, that's all I've got. I hope you like it. I think it's very interesting that we can expand in higher dimensions like this. Anyway, I'll see you in the next class. Bye.